Good afternoon, everyone. My name is Ankit Jain, and I am a software engineer with the AWS Search team, leading development efforts and for search performance and resiliency. I am also active maintainer for OpenSearch open source project and recently nominated to be a committer for Apache Lucene as well. Today, I am excited to share our ongoing journey of aggregation optimizations that is powering Lightning-Fas analytics in OpenSearch. When we started this performance optimization journey, we didn't expect such dramatic results. We simply focused on doing our best, diving deep, asking the right questions, and trying to understand the system better. And in the process, we ended up achieving far more than we imagined. We have fairly packed agenda for today. Let us start with a quick recap of aggregations in OpenSearch. Aggregations are a very good way of understanding the data at a high level without getting into the low-level details using visualizations. At a high level, OpenSearch supports three main types of aggregations. First one is metric aggregations, which can be used to calculate stats like min, max, sum, average. Then comes the bucket aggregation, which can be used to group and count documents like by date, terms, or ranges. And then comes the pipeline aggregations, which is something built on top of other aggregations using the output of the previous one as the input to another. So this is very similar to a shell, to a pipe operator in a shell. For today's talk, we will mostly be focusing on bucket aggregations, where we have seen the biggest performance wins. One of the most common bucket aggregation type is date histogram. Date histogram aggregation is widely used for many use cases. For example, analyzing web traffic patterns, monitoring application metrics and logs, visualizing sales trends, and many others. Here is an example of visualizing weekly date histogram aggregation. It groups number of visits to the website for each week over a period of 3 months. At a high level, most query DSL looks something like this. The size parameter is used for controlling the document hits that are returned as part of the search response. The aggregations are what power most of the visualizations we see in OpenSearch dashboards. And filter is used to narrow down to specific documents, which applies both to the documents being retrieved and for aggregation. We are mainly going to focus on this particular date histogram query for significant portion of our talk. This is monthly date histogram aggregation for the NYC taxes dataset to see the number of rides per month over a 12-month period from Jan 2015 to December 2015. The response will have 20 data points, which is the number of rides for each month. When we started looking at this query for the first time, it seemed pretty straightforward. I thought how hard it could be to compute 12 data points on a large set of data. But it turns out that this query was originally taking about 7 to 8 seconds. And whenever I start on try to understand the performance bottlenecks for a search request, one of the things that I try to do is I take that query, ingest the data set on a single node, and run that query in a loop. And then I collect flame graphs on top of that. And flame graphs are able to give you good insights into the expensive components of that query execution. Wider something is on a flame graph, more expensive that execution is. After looking at the flame graph for this particular query execution, I could understand that collection of documents is one of the most expensive part. So more than 90% of the time of this query execution goes in document collection. Then I understood more about how aggregation executes in OpenSearch. And that is when it all started making sense to me. Here is a look at the default execution flow. Right? Let's say we are querying for documents where status is equal to 200 and operating system is Android. Lucene handles the query and returns a doc ID set iterator by combining the doc ID set iterator for individual queries. The iterator is then passed to the aggregator, which reads the aggregation field using doc values for each doc ID and maps each document into the appropriate bucket. So in this example, we can see that status equal to 200 matches the document 1, 2, 5, and 700, and operating system is equal to Android matches document ID 1, 4, 5, and 700. When we try to combine these two iterators, we are only left with document ID 1, 5, and 700. Though simple, this approach is very elegant because it enables the creation of complex sub-aggregations. So think of it like a waterfall model where the document IDs are streamed after a query execution, and then they flow through each collector in OpenSearch, ensuring they are correctly mapped into the top level and sub-level buckets. For example, if you want to see the HTTP status code distribution for each month, status code can be a sub-aggregation for top-level date histogram aggregation. So looking at this flame graph, we were able to identify that the key bottlenecks for this query execution is the sheer number of documents that we are trying to collect. So this query was mapping to like more than 1 million documents. And then also the bucket cardinality, because as we collect more documents into the map, it results into more hashing collisions, which increase the collection time further. And this is where things start getting really interesting. So one of the first things I did was a little experiment, right? I was thinking, okay, what if we took our big query, which is querying the data for 12 months, and run it as 2 parallel queries, querying data for 6 months, right? Because in this case, the results are very, you can combine the results very easily, right? You will get 6 data points from one query, 6 data points from another, and you will have the result for the full query. And this did improve the time to 4 seconds from 8 seconds, but I got feedback from the community that this is indeed a zero-sum game, because we are trying to make the query execution concurrent. It is consuming more CPU for a single query execution, but at high throughput, this is not going to help. So after that, I did another experiment. What if we sliced it down to just 1 month, just for understanding it better, right? And the way we can do it is, we can run it as a query for 1 month. So where we say, okay, this is a range query on drop-off date time field, right? I think it should be for the month of January. So I think right now it says a year. And then we can track the total hits to true, right? When I did this, I noticed that the took time dropped to 162 milliseconds, right? Now, even if I run the same thing for 12 months in a serial manner, it will add up to 2 seconds. It has already dropped from 8 seconds to 2 seconds without increasing any concurrency. What just happened? So to understand better what just happened, we need to understand how Lucene executes this search request. So for executing this query, Lucene creates something called a range query. And while executing the range query, Lucene is able to identify that the search request does not have any aggregations, and the size is also 0. So instead of creating the doc ID set iterator, it leverages the count API on range query in Lucene. Now, another question arises. Why is the count API so efficient? To answer that question, we need to understand a bit more about the points index in Lucene. As we know, Lucene has multiple data structures for storing same information. Numeric fields like timestamp are stored in doc value as well as points index. While points index has been extensively used for query in OpenSearch, but it was never used for building aggregation before. To understand these improvements, let us quickly try to understand what a BKD is. Everyone here most likely knows about what a binary search tree is. It's a simple tree which has, each node has 2 children, and left subtree has all the smaller values, and the right subtree has larger values. And in-order traversal of such a tree will give all the data points in a sorted order. KD tree is something which is used for multi-dimensional data, like say 2D say points in a 2D plane. Each level partitions data on different dimension, like level 1 on x-axis, level 2 on y-axis, level 3 on x-axis again, and so on. So we can see in this visualization that the first one partitions on the x-axis, the second one partitions on y-axis, and so on. And gradually you can see that we are able to get all the points in separate paths, separate subtrees, which will allow for efficient searching for these points. BKD tree is nothing but a more efficient disk storage for this KD tree, ensuring minimum disk operations when we want to retrieve the data. Also, BKD trees are very efficient when they don't need to be updated after creation, which works really well because segments in Lucene are immutable. So to understand the efficient execution of this count API, we are going to take a very simplistic model of BKD. It's a single dimension, so we don't have to worry about multiple dimension over here. Each internal node has 2 children, which is not necessarily true. And those internal nodes are storing some metadata, like the range of doc values and the number of documents. And only leaf nodes store the data, the actual data, in this tree. Now let's say you want to count the number of documents for range query 351 to 771. So you will start at the top of this BKD tree, right? And you notice that the range on the top says 1 to 800. Now this range is, so this range is something which is not entirely contained in the range query. So you need to drill further into this tree. So the way to go about it is you do a recursive traversal in this BKD, and we are able to see that we need to go to only 2 leaf nodes. Other leaf nodes can be completely skipped because the only leaf nodes we need to visit individually is where the values 351 and 770 lie, which is in the 4th and the last leaf node. So eventually, the count execution is able to build the total number of document, which turns out to be 420 in this case, by doing this recursive traversal. So in this case, we can see that the subtree with document range from 1 to 200 is completely skipped, right? Because it cannot match a range query that has range 351 to 770. And some of the other internal subtrees, for example, this 401 to 600, we know this is completely contained within the query. So all the documents in this subtree are going to be a match. So using this approach, we are able to very efficiently compute the number of matching documents. And this is when we realized, wow, like this is so fast. Why can't we like just rewrite this original aggregation search request as filter query for all the 12 months? So we wrote it into like this range query for all the months, and this is what we observed in our benchmarks. So this is like more than 50x improvement for daily and hourly aggregations of date histogram across different OpenSearch versions. Now we need to understand why this gray bar, the one for minutely aggregation, behaves a bit differently. To understand that, we need to see what exactly we just did now. So we created the buckets in advance for the date histogram collection. We counted the leaves. We try to skip as many as possible. But we do all these things bucket at a time. We take, so let's say if you are requesting for 1,000 buckets, then we will do this exercise 1,000 times. And that is exactly what happens. So when you are requesting for daily aggregation on 10-day data, you have just 10 buckets. When you do hourly aggregations, it will be 240 buckets. And when you do minutely aggregation, I don't know how many it is, but yeah, we can probably multiply. But it's going to be more than 10K. So this is when we realize, okay, the approach that we just came up with, while it is good, but it is not able to do a good job when the bucket cardinality is huge. Also, if let us say we are collecting 100 matches over 1,000 buckets, it's probably better to just iterate over those 1,000 documents and use the default aggregation flow for collecting those documents. To solve these issues with the filter rewrite approach, we came up with something completely new called multi-range traversal. In this multi-range traversal, we are, instead of collecting the number of documents for each bucket individually, we do a single traversal of this BKD and collect the documents for all the buckets in one go. For example, if we assume that we have like 4 buckets that we want to collect the data for, and we have the same BKD as we had earlier, so our execution flow will look something like this. So again, we start from the top, right? And it's kind of a 2-pointer approach where the current bucket that we are pointing to is the first green one. And we start from the top of the tree, and we keep going down into this tree until we are able to collect the documents for this green bucket. The moment we hit a document that has value which doesn't fit in this green bucket, we move over to the next bucket. Remember, the in-order traversal in a binary tree, in a BKD, is going to be in a sorted order. So the moment, and that is what we are doing here. So the moment you hit a value higher than the first bucket, you cannot find any more matches for this bucket in this tree. So we keep iterating over the BKD in this manner until we are able to collect documents for all the buckets. And as you can see, that finally we are still able to skip 4 to 5 leaf nodes completely. While this might not seem much, But when we are thinking about BKD implementations in production, they can be really dense, and for every bucket, if you are starting from top of the tree, it might take a while before you get into the leaf nodes. And repeating that process for every bucket is not ideal. So once we implemented this in 2.14, we were able to reduce the latency for minutely aggregations as well. And in addition to helping the minutely aggregation, when we zoom into this benchmark, we can clearly see that it helps the daily and hourly aggregation performance as well by 2 to 3x. This optimization was very significant, and we contributed this back into Lucene as well, so that other search engines based on top of Lucene, like Elasticsearch and Solr, can also benefit from it. While this looks really good, it has limitations of its own. For example, if you have filter on a field that you are not aggregating on, then this cannot work, because the BKD does not have any correlation with the doc ID matches on some other field. Also, if you want to do sub-aggregation, it runs into the same issue. And if there are any documents, deleted documents for a segment, in that case also, we are not able to use this, because Lucene maintains deleted document separately in a bit set, and we are not able to account for that in this multi-range traversal approach. So let's take an example for this multi-filter query. So in this query, we have a filter on trip distance, right? So essentially, we are interested in all the rides that had distance from 0 to 50 miles, and then we want to do a monthly aggregation on top of that. Like, this can be a very common use case. So this is where the skip index comes into play. As part of Lucene 10, Lucene added something called skip index on top of doc values. So skip index is it's a data structure very similar to skip list. So on the bottom in this graph, you have like doc IDs from 0 to 100, right? And at the first level, you have so this is like block of 5, where we are like skipping every 5 documents, right? And we maintain the min and max values for that interval. And as you go higher in the skip list, you are able to skip more documents. When you are indexing the data in Lucene, you have an option to specify a sort field. And when this sort field, the field that you specify sort on, that is the order in which doc IDs are generated. So let's say if you take timestamp or drop off time, date time as the sort field, then so you will have a linear relationship between the doc IDs in that index and the value for the actual value for the drop off date time. And we can leverage this information to come up with another significant optimization. So as we were discussing earlier, in the default flow, Lucene executes the search request and generates something called doc ID set iterator, right? Now, what we can do over here is, so we take this query and we generate a doc ID set iterator on top of trip distance. So that will give us list of all the matching documents that have a trip distance from 0 to 50 miles. And then we can try to overlay that doc ID set iterator with the skip index for drop of date time. And by doing that, we will be able to skip the individual doc IDs very efficiently. And the reason for that is, for example, if we again take that interval from 351 to 750, so what we are able to say that for document 35 to 76, this is the value of the drop of date time. And we have the individual doc ID from our doc ID set iterator. So if all of these values fall in a single bucket for the date histogram, then we can efficiently say, okay, all the document IDs in the doc ID set iterator between this doc ID to this doc ID will go in a single bucket. And we can count all those document IDs very efficiently using a CPU instruction called pop count. So pop count is a CPU instruction like short for population count, and all these doc ID set iterators are backed by a bit set, which is nothing but bunch of long in memory. And this pop count instruction can efficiently count the number of set bits in a long. So using that, we tried a POC of this approach, and we are able to see up to 3x improvement. While I know it is not as significant as 100x for the date histogram, but it is still very impressive because of the wider use cases this optimization is applicable for. In addition to skip list based optimizations, we are also looking at vectorized execution. As we discussed earlier, we are processing aggregations document at a time, which is not a very efficient approach. Instead, especially for some scalar function executions, for example, if you want to do a aggregation for sum, min, or max, that is something which can be very easily vectorized. What we can do is we can load, instead of doing one doc value, we can load hundreds of them and execute them in a single instruction using SIMD. If none of these work for your use case, then we also have an option of star tree index. One of the disadvantages of star tree index is that you need to understand your use case beforehand, because this is something you need to create at indexing time, and only then it is available for search. But if you understand that your use case very well, and star tree is something that works for your use cases, then this can also provide very significant speed up. These are some of the notable GitHub issues that we had while working on these performance improvements. So feel free to check these out. And if you have any feedback, feel free to tag me or comment or anything else. With that, I come to the end of my presentation. If you have any questions, do let me know.